So we're looking at controlling motion on a molecular level. We want to be able to do that on command as well. So when we mean a command, we can apply some sort of external input. That could be applying light, it could be changes with pH, it could be using some redox chemistry, and basically that acts as a switch, so we can control that we can turn that molecular motion on and off.
For the last 20 to 30 years, there's been interest in what are now called, I guess, molecular machines. And this culminated in the recent award of a Nobel Prize in 2016 to three chemists. And it's all about really trying to replicate what we see all around us in the macroscopic world. Can we build really, really tiny machines on the nanoscale? And will they perform the same functions? Now we're thinking about different types of molecular system that can be incorporated into a device or can be termed as a molecular machine. And ball bearing type molecules have been less explored so far. So this is where our research fits in, or our approach in this is to really expand the toolkit of examples of molecular machine. And so the idea of having a metal as the ball bearing, just one atom at the centre of a molecule, which other parts of the molecule can spin around it, that would be a ball bearing, but on the molecular scale.
What we're doing in particular with our system is we're looking at controlling the rotary motion about a ball-bearing axis of a cobalt metallocene. So metallocene are sandwich complexes, and in the middle we've got our cobalt atom, and then it's sandwiched by two aromatic rings. The switch that we're using in our case, our chemical input, is changing in pH. So we've designed our system so that at neutral pH we have nice free rotation about that metallocene axis, and when we lower the pH we have then designed our system so that we increase its interactions with itself. It starts to hinder the rotation about that metallocene axis. We can probe this rotation about the metallocene axis is using NMR, and one of the ways we need to do this is cooling it down to lower temperatures, and that's where we can start to see the different conformations that our metallocene is taking. So what we did is we recorded several NMR experiments starting at 25 degrees Celsius. We went down to minus 35 degrees Celsius. Every 10 degrees we'd run another NMR experiment, and we can overlay those spectra and start to really map out the shifts and the peak broadening, the shifts, the splitting that we see by overlaying them. With the help of Cecile and the NMR team here, I was taught how to really tailor the conditions to fit our molecule perfectly, and what is actually really quite a complex molecule.